Swati, we can start.
Yes, sir. Good evening, everyone, and welcome back to day 7 of this FDP, jointly organized by EICT Academy and MNIT Jaipur. We are fortunate to have Mr. Alok Kumar Singhal, sir, as distinguished speaker. Sir has completed higher studies MTech from MNIT Jaipur and currently working in ISRO SAC Ahmedabad as head Setcom and Navigation Antenna Division. Sir has more than 20 years of experience and research and development in the field of antennas for space communication. Under Dr. Singhal sir's guidance, various projects have been completed with and without the collaboration of reputed IITs and NITs. Sir's research areas include microstrip patch antenna, focal array fed and reflectors, active patch antennas, and many more antennas for satellite communication. Thank you very much, sir, for accepting our invitation as a distinguished speaker. I request you to kindly take over the session. Thank you, sir. Hello.
Sir, your voice is not audible.
Hello.
Hello. Yes, sir.
Hello, I'm audible.
Yeah, you are audible now, sir. Thanks.
Yeah, voice is clear.
Yes, sir.
Yes, sir.
It's clear.
Okay.
Okay.
Yeah.
Yeah.
इसमें बस तीनों लगा
Sir,
Hello.
yes.
Yeah. Should
Sir,
I
can we,
start?
sir, we have a question. Can we record this lecture or not?
You can.
Okay. Thank you, sir.
Yeah.
Yes, sir, we can start. Yes, sir.
Yeah. Okay, my voice is clear.
Yes, sir, your voice is clear, sir.
Okay.
Yeah.
Yeah. Actually, I'm Alok Singhal, working in SEC, ISRO Ahmedabad. Just I completed BTech MTech from MNIT Jaipur and then joined in 2002 as a scientist. Now I am head in the Setcom and Navigation Antenna Division. So mainly work are related to all types of antenna, that patch antenna, helix antenna, horn antenna, and reflector antenna, phaser antenna, beam forming antenna. So as you know that, okay, antenna is a transducer that convert guided wave into radiated wave. So antenna is a passive device, or we can say that it can be used as a transmit mode and receive mode. So in antenna itself, we cannot say that, okay, this antenna used for only transmit or only receive. That decided by the backside of the elements, maybe amplifier in terms of SSPA or TWTA, or low noise amplifier in terms of receive antenna. So antenna can be configured in transmit only, receive only, or both. So antenna terminology, if I say that, okay, these are the basic characteristics of antenna, that characteristic impedance, reflection coefficient, VSWR, return loss, and Smith chart. So initially 4 parameters correlated with the initially parameter that we want to design the antenna. So how much power accepted by the antenna? So all character impedance, reflection coefficient, VSWR, return loss. Reflection coefficient, VSWR, return loss, all are interrelated. And Smith chart is the property in which we see the impedance versus frequency. That what is the frequency at it is resonating, if it is a resonant structure. So mostly reflector antenna is not resonant structure. Otherwise, all types like patch antenna, helix antenna, horn antenna may be wide, but reflector antenna does not depend on the frequency. So feed of the reflector antenna is depend on the frequency. So feed can be designed as a transmit and receive or broadband. Another parameter, insertion loss, how much power you are losing up to the radiation. That means antenna accepted or antenna power is Pi. Some power will be reflected, PR, P accepted. So how much antenna is. So generally we see the return loss. Initially, when we design the antenna, that only return loss we see the, on then we are saying that, okay, my return loss is better than 10 dB, 20 dB. So then my antenna is working. But not, this is not the correct explanation that, okay, I am getting return loss better than 10 dB or my antenna is radiating. But how much power or in which direction antenna is radiating? And some losses due to dielectric material or conductive material. Isolation is the parameter in which antenna can be used as a transmit or receive. If antenna is using for both function, transmit and receive, because transmit power is very high, in that scenario, receive antenna, if I am talking that, okay, antenna is pumping or taking 100 watt power, but receive side, LN is minus 100 dBm, minus 70 dBm. So isolation is very important to get whether it's a shear aperture antenna or if it is broadband antenna. Broadband antenna is single port that you are getting transmit and receive. So no isolation you can get, but by using diplexer, we can get the isolation. So isolation is the very transmit and receive. Bandwidth point of view, that, okay, antenna bandwidth is given by mostly persons are given by return loss. Okay, I am getting 30% return loss, but in terms of XL ratio, in terms of gain performance, in terms of EOC, age of coverage requirement, that bandwidth will be different. So overall bandwidth means return loss, XL ratio, EOC gain, and also beamwidth should be in that bandwidth. And antenna specification, if we see that, okay, what are the input parameters required to design the antenna? So first is the frequency band in which we want to design. Function, it should be used for transmit only or receive only, or transmit and receive only. When we design the antenna in transmit mode, our main important parameter is the power handling capability of the antenna. Receive, definitely power handling is very less. Transmit and receive, so both transmit and receive means isolation is very important, also power handling capability of the antenna. Another parameter, return loss, gain, how much power is transmitted by antenna, and polarization is very important factor which give the information of electric field, that electric field is in which direction or in which sense of rotation. So based on the fashion of electric field variation in the direction of propagation with respect to time, antenna categorized in two type of polarization. One is linear polarization, another is circular polarization. Co-polarization and cross-polarization. There are other terminology. Co-polarization means that we want antenna in particular fashion in linear or circular, that we want electric field as a polarization that called. So cross polarization is an unwanted component of electric field in which other direction or in other sense of rotation. If linear vertical antenna is polarization means co-polarization. If I say that okay, antenna is RSCP, it means cross polarization means antenna is LSCP. How much power is pumping by the antenna in LSCP sense of polarization, and axial ratio is the property in which that okay how much circular polarization purity, that ideally we cannot get circular polarization. Difference in linear and circular polarization, one important parameter, that electric field, type of electric field variation magnitude will change in linear polarization, what in circular polarization tip of electric field vector will be always constant and it will rotate. So constant electric field in circular polarization and linear polarization, electric field, tip of electric field vector will vary, amplitude will vary. So bandwidth point of view, that okay, like impedance bandwidth, that at resonance frequency we are getting good return loss, but below the resonance frequency lower side and upper side, that response impedance will not perfectly match with the frequency. So in that case, some cutoff. So like 10 dB, 10 dB return loss means 10% reflected power. 20 dB return loss means 1% reflected power. So 10 dB generally when we design the antenna in ground application, that okay 10 dB return loss is sufficient. But when we design the antenna in spacecraft or satellite communication or because satellite will work in approximately 10 to 15 years. So we design the antenna more than 17 dB return loss. So 17 dB return loss means 2% reflected power is accepted. It means antenna should be 98% power of the input. Similar way, axial ratio bandwidth. Okay, at particular frequency you can get 0 dB axial ratio or close to 0 dB, but below the resonance frequency or in that case, acceptable limit is 3 dB axial ratio. 3 dB axial ratio means if I say in voltage term, that 70% of voltage or half power point means power is half. So you will get ellipse. In that case, axial ratio will be, so major axis and minor axis ratio is 1/2. Major axis is 1, minor axis is half. In that case, axial ratio bandwidth. So both should be equal, not only impedance bandwidth. So axial ratio bandwidth is if I am getting 10% impedance bandwidth, but I am getting axial ratio bandwidth only 3% or 2%. In that case, I can use only 2% bandwidth for both. Now, antenna gain, isotropic antenna, omnidirectional antenna. So antenna gain is not active device. So like an amplifier, that okay, antenna gain is voltage output upon voltage input. So we are increasing the power in particular direction. Ideally, in isotropic antenna, gain is 0 dB. But when we squeeze the power in other direction and expand in other direction, that means directional antenna. So different patterns you will get. So mostly antenna pattern are cosine pattern, but ideally speaking that okay, I want flat type pattern. Flat type pattern means I want constant gain, but inherent property due to our signals is time nature. In that scenario, that antenna, okay, antenna in XY plane, Z is the direction of radiation. It means theta 0. In that case, we will get cosine pattern. So categorized by high gain antenna, we use 20 dB, more than 20 dB. So we mostly use parabolic dish antenna. Medium gain antenna 10 to 20 dB. That we use horn antenna, helix antenna, and Yagi antenna. wave antenna. Now, if I want to increase the gain, then I will use the array antenna, maybe element, helix antenna, horn antenna, or patch antenna. Now, this typical 3D radiation pattern that we know that okay, at main loop means theta is equal to 0 in z axis if antenna in xy plane. So aperture plane is xy plane and theta 0 is the main loop. And 3D beamwidth means half power point, that what is the 3 dB below gain angle as a conical angle. First side loop, second side loop, third loop depends on the configuration of the antenna. And back loop means front to back ratio, means generally antenna radiate and back side. So front to back ratio is very important factor that we want to some active element behind the antenna. In that case, if antenna is radiating more power, or if run to back ratio is 20 dB, it means 1 by 100. It means 100 watt power is in both sides, that 1 watt will be reflected, or 1 watt in back side. In that scenario, that okay, due to 1 watt, that power density or near to active elements, that performance will change. So that is the back loop radiation that we want to reduce as minimum as possible. So 30 dB or 20 dB depends on the link calculation when we are putting the active elements behind the antenna. These are the basic term: main loop, minor loop, back loop level, half power beamwidth means. Okay, polarization is given by the really it's given by the electric field. So polarization of a wave, the curve means tip of the electric field vector traces out with time at a fixed observation point. So if tip of electric field vary along the linear fashion, the linear polarized. If tip of electric field vector in circularly or rotating. So it might generally in circular polarization sense that direction of radiation or direction of propagation, we put our thumb in the direction of radiation, then our direction of finger, rotation or orientation of direction of finger will give the picture. It means if I am using right hand, or our electric field rotate according to right hand, that means right hand circular polarization. Or if it is in left hand side or left hand, that means left hand circular polarization. Based on that, clockwise or anti-clockwise. So generally our thumb should be in the direction of the radiation, and our rotation or orientation of our finger will give the direction of RSCP or LSCP. And elliptical polarization means constant field will not exist in that scenario. Major axis and so linear polarized, circular polarized, elliptical polarized. Now, how we get again? Yeah, axial ratio. It is the measure of ellipticity of the EM wave. So it is defined as the ratio of major axis and minor axis. So ideally, circular polarization complete constant electric field will not get. So axial ratio ideally it is 1 in numerical value and 0 dB in decibel value. So axial ratio is 1 circular polarization, and if minor axis is 0, it means in that scenario axial ratio will be infinite. So linear polarization, that is called linear polarization because electric field variation only in one direction. Now, how we get circular polarization? So just by explanation of Lissajous figure, that okay, these are the two components that CRO works, that two horizontal plate and two vertical plates. So EX is applied on horizontal plates and EY is applied on vertical, X and Y. So like that, if I say that this is the EX and this is the EY, it means deflection of electronic beam in CRO. That same explanation in circular polarization in electromagnetic theory, that okay, EX is applied on horizontal axis or EY is applied on Y axis. If I say that EX and EY. Both are sine wave signal that we will get linear polarization if Ex is E0 cos omega t, means that Ex is equal to E0 sin omega t plus pi by 2. It means Ex is leading in that scenario, that maximum at 0, but Ey is 0. So at 0 time, that it is 1 or equal to E0, but E by it is 0. So both are superposed at that point. And then when we move forward, that sense of rotation is like this. It means you will get RSCP or anti-clockwise. So that Ex should be 90-degree phase lead, or we can say that Ey should be lag by Ex. In that case, both you will get circumpolation RSCP and direction is anti-clockwise. If I put a thumb in the center region, orientation is anti-clockwise or RSCP. Similar way, in this fashion, if Ex is E0 sin omega t and Ey is equal to E0 cos omega t, it means E0 sin omega t plus pi by t. In that case, Ey is leading or Ex is lagging. In that case, polarization is left hand circopolarization and direction is clockwise. Okay. E plane and H plane. So generally we see that, okay, where is the electric field and magnetic field of the patch antenna? That if I say that x axis in blue direction, y axis in right direction. So Z will be outward of the screen. In that scenario, if antenna is feeding by the coaxial feed at this point, not in the center, in that case, this will be length because radiating edge will be width. So in that case, half cycle variation. So L should be lambda by 2. So this is the minimum half cycle variation that this work as a antenna or as a radiator. So along the width, it will radiate and constant field variation along the width, but along the length, it is sinusoidal variation. So along the length, there will be no radiation. In that case, we can say that electric field in X direction, Ex, and mode is TM01 mode. So in this figure, if I say that X is below, Y is in right direction, mode will be TM. And due to some fringing field, and E field means Ex at phi is equal to 0. That is called copole, because direction of electric field in X direction, phi 0 means XZ plane. Now cross pole, E field, if Ex is phi 0, that H field will be orthogonal. So again, Ex component in Y direction, that is phi is equal to 90. Phi 90 means YZ plane. So that is called as a H field. So both are copole. Ex at phi is equal to 0 and Ex at phi is equal to 90, that E and H field. Now what is cross pole? That ideally speaking, if probe position in the center, that no cross pole component will be exist, but due to TM02 mode, we will get some components in Y direction, but magnitude will be very less. So Ey component is the cross polarization. So Ey at phi is equal to 0 means some component in electric field along the length will generate, but not very, if I say that 20 dB or 30 dB down, 20 dB means 1 by 100, it means 100 watt or 100 intensity of electric field in X direction, then one numerical value will be in Y direction. If cross pole level is 20 dB, then in that case, Ey at phi is equal to 0. It means that is called cross polarization of electric field. Similar way, H field, Ey and phi is equal to 90. So E plane along X Z plane due to Ex component only. But Ey is the cross polarization. So cross again EY component in electric field direction, that is called cross pole. That means EY is equal to EY at phi is equal to 0. So E field and H field. Fundamental mode TM10 mode due to level to cycle along the length. This is the first dominant mode that antenna or patch antenna is a we can say that okay, it is radiating, because below this no wave or no part of sinusoidal signal cannot work as a radiator. So one means half cycle variation, number one half cycle variation along x-axis, and TM01 means half cycle variation along y-axis. So along the breadth, voltage is maximum, current is minimum due to open ends. So generally antenna when we define the okay how antenna radiate, patch antenna radiate, that means by general transmission line theory. So a line if along this width and along the length. So I explain this behavior in this fashion that okay, plus B and minus B. So this is the first one half cycle that plus B and minus B. Now due to plus B patch in that case, so vertical and horizontal component like this, and vertical component will be cancelling each out because plus B and minus B direction is changed. So only horizontal component or electric field in the parallel of the aperture or parallel of the patch plane. It means there is no electric field variation along the Z direction. In that case, one direction will be right direction or parallel to plane of the patch, and in next half cycle minus B to plus B direction will change. So electric field towards left side. So this is the left side and this is right side. So it will make a loop and then antenna will resonate or antenna will radiate in the Z direction. So electric field variation along X or Y axis, but radiation will be in Z direction. So there is no component in the direction of the radiation, and magnetic field will be orthogonal. So then in the center, it means TM10 because half cycle variation along the x-axis, and in this figure's right side that okay half cycle variation because proposition at this, so TM01 mode. Okay. Y cross polarization in patch antenna. Now TM10 contribute to copolarization. TM01 means the voltage at the feed point is 0, so mode will not be generated. And this is the Y that field is in the middle along width of the patch. It means along the width, if I put a connector or proposition at the 50 ohm location, so TM01 mode will not excite, but TM02 mode major reason for cross polarization, since the voltage at the feed point is not 0, some impedance, and the mode unwanted get excited. So major reason of the cross polarization in patch antenna due to TM02 mode, but with very less value. So we can reduce this by different techniques. Now near field distribution in patch antenna, that along the length this is the half cycle variation, but along the width it is a constant variation. So XZ plane and YZ plane, this is the pictorial view that antenna radiates along the width on YZ. This is the surface current distribution of circumpolation antenna that we want to radiate in all sides. So this is the RSCB polarization behavior of the antenna, that antenna will radiate as a truncated with the nearly square patch antenna. So antenna will electric field will rotate. A simple empirical relation to design the antenna. Line extension delta L and electric field variation, that half cycle variation, positive half cycle, and towards down electric field in the below. So at the edge, electric field direction will be opposite and vertical component will be cancelled. Yeah, this is the typical radiation plot of the fundamental mode. So antenna provide cosine pattern. That antenna gain is decided by the size of the antenna also. That generally we design the antenna on PTFE material which comes from 1.5 3 or 3.5 dielectric constant, and some materials are glass epoxy material which covers approximately 4 to 4.4, and some materials with combination of ceramic plus PTFE which comes category from 4 to 4.5 to 6 or 7 or 8. But more than this, generally only ceramic are used. So based on the antenna gain requirement, we choose the substrate material. That okay, if I want single element gain 9 dB or 8 dB, I will use as a air dielectric, because this is the because size will be of the antenna is given by the lambda by 2. So lambda g again equal to lambda in case of air. So this is the maximum antenna. So a patch antenna maximum gain can be achieved by only dielectric or only air substrate as a substrate. So air we use foam material. The dielectric constant equivalent to 1.00 something or near to equivalent, and loss standard is very less, 0.0002. Density is also less, but in space applications generally we avoid material. So we use honeycomb, quartz honeycomb material, which is in honeycomb structure as a dielectric constant is very small, 1.00 something. And when we use, okay, I want to design the antenna gain near to 6 to 8 dB or 9 dB. We use DK 2.2 to 3 and 3.5, not more than this. But in glass epoxy, we can now get more than 5 dB gain, because due to dielectric constant 4.4, so that's why size will be less. So antenna gain is given by a 4 pi a by lambda, simple. So area, you are reducing the area due to dielectric constant, because dielectric constant is generally given high. That means lambda g will be less. In that case, lambda 0 by g by 2 is also less. In that case, total area of antenna at particular frequency. If I say that 1 gigahertz or 2 gigahertz, that similar antenna is designed on air or low dielectric constant, size will be more. So antenna depends on the antenna gain. We decide the dielectric material. Or if generally if we see that okay in GPS or IRNSS application, antenna gain we don't want more. Our antenna gain requirement is 2 dB. So that we use ceramic material that DK 10 or 20. So size will be very less. If I say that L-band antenna, or if I say that generally GPS antenna are size by 1 inch by 1 inch. So 4 mm like that. Similarly, in IRNSS application, we use ceramic or DK 10 or DK 20. In that case, gain is up dB. But advantage of this low dielectric or high dielectric material, dielectric constant material, that size is less. It means low gain antenna. That means your beam width will be wide, because gain and beam width will be constant. So when we are giving the low gain, it means you are increasing the beam width. So this is the advantage, that we don't want to link with the both side. In that case, we want to communication up to 70 degree or 60 degree or 80 degree, up to theta degree. But theta 60 or 70 or 80 degree, because similar way in GPS also. And these are the some basic configuration of circumpolation and patch antenna. That they are dual feed techniques. It's a EM coupled patch antenna. That single feed with necessary degenerative modes. So generally if single feed is used, then definitely you can get two modes. Degenerative mode means TM10 and TM01 mode, but at a single frequency. But when we use dual feed, that you can control individually modes by giving the excitation at dual feeds. So by using some, this is the Wilkinson, this is a hybrid power divider. In that case, it is inherently isolation between these two ports will very good, better or approximately 30 dB. So why we when we are using independently, okay, dual feed, but really I need isolation if I am using T power divider like in second figure. So XLSO performance will be in hybrid configuration, because when isolation is poor, in that case some power will be reflect back, because in generally T power divider isolation is very poor or order of 6 dB only. So if due to at this point some mismatch is there, power will be reflect back, and due to 6 dB isolation only, that it means 6 dB isolation means 25% power may add up in this port. So impedance unbalance and also phase that we want 90 degree, it may also imbalance. In that case, acceleration poor in T type of power divider. But in hybrid case, when isolation is 30 dB, if some power is reflected back at this port, that means you are getting some interference at this port 1 by 1000. If isolation is 30 dB, it means very negligible effect of amplitude variation at this port due to this, but because of isolation between these two ports. So this is need to increase the XLSO capability. Similar way in single port, very less XLSO bandwidth. So to increase the XLSO bandwidth, this is a truncated corner patch antenna. Why? This is fed up. This is the EM coupled patch antenna. So EM coupling by achieved by this line, but impedance matching is done by this quarter wave transformer, and then this is again the 50 ohm line. And if I want to increase the XLSO bandwidth, I use a stack patch configuration in truncated corner. So XLSO bandwidth also increase and return loss bandwidth also increase. Yeah, the other structure to get circumpolation is like power divider lambda 4 length extra to address this A-speed technique, 90 degree hybrid, and these are single feed point that by diagonal feeding or by nearly square patch antenna, that diagonal feeding, that at that point both mode will be exist, because L and W both should be equal, because some slightly difference depends on this difference. L plus delta L, width should be L plus delta L, that is called nearly square patch antenna. In that case, TM10 and TM01 mode at a single frequency. So TM10 mode will give the plus 45 degree leading, and TM01 mode will be minus 45 degree lagging. So total difference is 90 degree, but equal amplitude, but at a single frequency. So control of this delta L variation, we can control the loop in the Smith chart. If I increase the delta L, then loop size will increase on the Smith chart. In that case, you will get return loss bandwidth will be good, but XLSO bandwidth will be very less. So generally, when we design a nearly square patch antenna, that loop should be as minimum as possible, that we can get the XLSO good, but also return loss bandwidth. So both are independent. Means if you are increasing the return loss bandwidth, you will lose the XLSO bandwidth. So both should be equal. It means loop size should be such that axial ratio and return loss bandwidth should be equal in nearly square patch antenna. Another configuration like that, this is slot in the antenna at the center and A speed, in that case W or L, both should be equal. But again, a single point from the edge, but at this edge, impedance should be matched. Generally, edge impedance, radiation impedance at the edge is free space impedance, 120 pi. So depends on the dielectric constant of the material. It may vary from 250 ohm to 400 or 500 ohm. So radiation resistance also depends on the width of the patch antenna. If width is less, radiation impedance is less. Like this is the truncated corner patch antenna and another circular patch antenna with the stuffs at the end. Yeah. These are the some basic geometry: triangular patch antenna, square patch antenna, circular patch antenna. And this is the LSE patch antenna on DK 20 for S band. This is a hybrid, and this is a Wilkinson power divider. And chip resistance is used in Wilkinson power divider of 100 ohm to get the. So this is the ohm line, and then this is the √2 Z0. Length is λ4. So as per Wilkinson power divider theory, and this is the 50 ohm line, this is the 50 ohm line. Now edge impedance is very high, close to 250 or 300 ohm. So it is matched with the quarter wave transformer. So this is the quarter wave transformer, very less. So impedance from 50 to 250 ohm. So this is the length of λ4. Again, this is extra length. So in that case, antenna is LSE, because signal from this point to this point, antenna, this edge will radiate. First radiation. After that, due to delay in this side, antenna will radiate from this side. In that case, antenna is LSEP. And this Wilkinson power divider is some reflection 25 dB or 30 dB down signal enter in this side due to some mismatch at that point. So isolation is good. So in this configuration, you will get very good axial ratio. Also return loss bandwidth. Yeah. This is the dual beat patch antenna with the stacked configuration. In this EM coupled, and then axial ratio is good, approximately 25 degrees cross polarization. Again, RSCP to LSCP will give the picture of axial ratio also. That axial ratio means if antenna is RSCP, means this is the copolarization. If I see this antenna as a LSC, because this is the nearest point and this is the farthest point, which is λ4 extra length. Now, so this is after that signal radiate from this edge. Just I am talking only. Okay, if anybody wants any question, please stop me and then he can raise the. So if anybody wants to any information related to this type of work, or he can stop me and hello, hello, hello.
Yes, sir, you are audible, sir.
Yeah. So give me message to me to participant. If anybody wants any question, and he can or he can ask the question.
Yes, sir.
Yeah. Okay. So in that case, if we see this picture of this geometry, antenna is LSCP, because first radiation from this side, and after that antenna will radiate from this side with lag of 90 degree, because length is extra λ4. And this is the quarter wave transformer. This is the 50 ohm line. Then this is a 70 ohm line with length of from this point to this point is λ4. Now this is again 50 ohm line, and this is the quarter wave transformer which matched. Now in previous slide that you are observing that, okay, why this is the width very less and 50 ohm line width is large. Actually, one question is that, okay, this is the 50 ohm point and this is the 70 ohm line, root 2 Z0. This is the 100 ohm chip resistance. This is again 50 ohm line. This is again 50 ohm line. Now, why this is width is very less? Second figure, in this case, this is again 50 ohm line and this is 70 ohm or root 2 Z0. This is again 50 ohm line. This is 50 ohm. Okay. Now, why this is width is large? Question is that this is the single layer antenna. Radiation impedance is approximately equal to 125 or depends on the directive question, maybe 250 ohm or 300 ohm or 350 ohm. So from impedance transformation from 50 to 300 ohm, impedance is large with respect to 50 ohm. Maybe 150 ohm by square root of 300 multiply 50. So approximately 150 ohm or maybe depends on the radiation resistance. So when we increase the impedance, width will be less. So that's why the width is less in this case. But in this case, lower patch and upper patch. I'm using upper patch also, that due to both combination lower patch. Generally, patch antenna is a parallel RLC circuit. So if another patch is above the lower patch, in that case, total impedance will be low. It means at this point, at the edge, due to parallel combination of RLC circuit, total impedance at that will be less or equal to 10 to 15 ohm or 20 ohm. So that's why I am using from 20 ohm to at this point 50 ohm. So width, it means this is approximately 35 ohm impedance. It means width is large and length is lambda by 4. So using this upper layer patch antenna, that I am increasing the bandwidth because the quality factor will be low. Because when we use lower patch and upper patch, that means total quality factor will be low. In that case, bandwidth will be increased. Or another explanation is that stagger tuning, that lower patch antenna resonate at single frequency or lower frequency and higher upper patch antenna at higher frequency. So depends on the dielectric material in between lower patch and upper patch. So mostly lower patch is we are getting good return loss bandwidth from 2.3 to 2.9. We are getting 10 dB return loss bandwidth, and XL ratio also order of 1 dB over the bandwidth and radiation pattern. Now again, RSCP and LSCP. If this antenna is LSCP, cross polarization level is RSCP. So this is the RSCP pattern. It means cross polarization. Now any relation between RSCP to LSCP which correlated to XL ratio. So generally difference between co-pole to cross pole, like that in this figure, that you can see that 7 dB or I think 9 dB came at RSC or LSCP antenna. This is the LSCP antenna. So we are getting 9 dB or probably 8 dB, and this level is minus 15 dB. It means total difference is 23 dB or 24 dB. So one relation between this cross pole difference to XL ratio. So 24.8 minus 20 log XL ratio. So like that, difference is 15 dB between LSCP to RSCP. That means XL ratio will be 3 dB. Now in this case, this difference is 25 dB approximately. That means XL ratio is 1 dB. Means by the relation 24.8 minus 20 log XL ratio. Dominant mode TM by explanation that equal amplitude, orthogonal axis and 90-degree phase difference. Another development we have done that concentric dual band circumpolar antenna S-band. Yeah, this is the S-band antenna design on decay, high decay, and this is the quad loop antenna. Means this length is lambda 4, and again by using sequential rotation, these are the feeding points. So direction of is LSCP. In that case, this is the feed network behind the ground plane and excited by 4 points like a quarter flare configuration. So if this is the zero angle, this is the minus 90, minus 180 and minus 270. So field is also rotating. In that case, acceleration is very good because you are cancelling the cross polarization level at a element level. And advantage of this concentric dual band antenna that okay, I am using unwanted or unradiated zone of L band antenna because L band antenna is outer antenna, S band antenna is put in non-radiating zone. So performance are optimized in that scenario. But main advantage of this concentric configuration that phase center generally when we are multiple frequency in IRNSS, we are using L and S band. Now L and S band, L band antenna phase center is different, or S band antenna. That means you are losing the accuracy because X, Y, Z and T will be due to non-concentric phase center. So phase center is a center point. So in this case, XY value of both phase center value at L and S band will be same, but Z may be different. So Z will be compensated by putting the value. Okay, I know that what is the variation in Z. So I will incorporate this Z value in the programming, but I cannot adjust X and Y value. So you will get exact position accuracy in this type of configuration of the antenna. Yeah. Again, high dielectric material, patch antenna, truncated corner, nearly square. Another development that okay, S-band antenna on DK10 and truncated corner patch antenna by keeping, because of this is the center. So by sorting or cutting in the center of the L-band antenna, we can get good performance for both L and S band. For RSC polarization, return loss better than 10 dB and acceleration less than 3 dB over the L and S band. L band proxy and this S band antenna on DK20 ceramic material. Okay. TM10 and TM30 modes are used. TM10 mode for L5 band and 30 mode for S band. So by keeping this is the total length for L that create TM10 mode, and this is the TM30 mode. Now dual feed for both band. So at L and S band, antenna is rotating, but how I can get equal amplitude at L band, also S band with 90-degree phase difference. So we designed a broadband power divider by using some stuffs that at LSCP and RSCP at this position. So this is the green is the broadband power divider at L and S. This is the measured return loss better than 10 dB, and per axle radiation performance also measured. And one development dielectric generator antenna we have done, but mostly we avoid the dielectric generator antenna. Generally, alignment is very difficult. Mostly we tried that. Okay, this is the Wilson power divider dual feed dielectric generator, similar performance better than patch antenna, but again it's a because due to very dielectric high dielectric constant DK10 or DK20, that position of the DRA. So in that case, axle ratio performance, even pattern symmetry, we are getting good and size is also 38 by 38 by 15 mm. But again, in mass production related things, this is not advisable. Uh, Only dual antenna, okay, it is very simple job, but when we are moving in mass production, it is very difficult to position or alignment of the field network. Field distribution and rear antenna. Now, again, to increase the axial ratio performance, that single patch antenna, 4 fields were excited with same magnitude and phase sequentially rotated by 90 degree, 0, minus 90, minus 120, minus 270. This was achieved by delay line in the Wilkinson power divider. So this is the again a good development that okay, this is the feed point. By using this program, 1:2 half power R given by this power divider, again 1/4. So at these 4 points, power is 0.25 watt. If 1 watt is at the input, it means equal amplitude but phase difference 90 degree. So in this configuration, this is the one angle 0 or equal amplitude. If I say that this is the with respect to from this point to this point, power division is minus 6 dB or 1/4 means minus 6 dB. So S, if I say this is the one port, 2, 3, 4 and 5. So I will say that S41 will be minus 6 dB, but with reference of some angle. So if I say that this is the angle 0 because this is the nearest point. So minus 6 dB with angle 0. Now this is the lambda 4 length extra. It means minus 6 dB minus 90 degree. Similar way, this is again minus 6 dB minus 180 degree. From this point, if length is x and this length is x plus lambda by 2. So this power divider is similar to this power divider. It means if this length is from this point to this point, length is x, it is x plus lambda by 2. It is 180 degree phase delay from this point to this point. It means minus 6 dB minus 180 degree, and this is the minus 6 dB and minus 270 degree. Now field is rotating according to this in right hand sense of the polarization. Now I will explain that okay, cross polarization cancellation in this configuration how. Yeah, another helix antenna is inherently circumpolarized antenna. That C is equal to pi d, that we know L is equal to A square plus C square. But important is that these are the work as a normal mode and axial mode. So generally we use normal mode propagation. In that case, sometimes we use this cup type arrangement to reduce the mutual coupling between elements. And the pitch angle means this alpha is equal to S by C. So S by C generally is this angle should be 10 to 14 to get good axial ratio. But a limitation of this helix antenna is that we cannot get more than 20 dB because when we increase the turn, that at the end of the turn, 20 ton or 15 ton or 18 ton, that current is very less. That means it will not contribute the radiation. So maximum gain can be achieved by the helix antenna is 18 to 20 dB, not more than this. So when we increase the antenna gain or increase the gain, that we need array environment. Now this is the quad flux antenna. In this antenna, beauty of this antenna that antenna pattern can be controlled. It means 4 helix are rotated in the manner that okay, 4 helix are rotated and 0, 90, 180 and 270. So axial is a performance and circumpolation. But again, this is not advisable for high gain antenna. So mostly 10 dB, 12 dB gain we can good achievable performance. But beauty of this antenna that we can control the radiation pattern by adjusting of the dia and height of the single turn. So mostly we get the cardioid shape pattern or flat type pattern with good acceleration performance in wide beamwidth. Now, why we need array antenna or phase array antenna? Now, if I see the patch antenna performance, okay, I can get 9 dB or 9.5 dB gain by a single antenna. Now, to increase the gain, I want to or increase the gain means in particular direction. So passive array antenna or phase array antenna. So increase directly in particular direction. A phase array antenna is a composed of the lots of radiating element, each with a phase shifter or digital or attenuator. Themes are formed by shifting the phase of the signal emitted for each radiating element to provide constructive or destructive. It means number of elements is decided uh, based on the requirement of the array gain or antenna gain. Now, like that, mostly patterns are cosine pattern. So formula is simple that cosine pattern cos is power k. Now, if I put k is 0.7, element gain will be 6.8 dB gain. Q value is 0.8, antenna directly will be 7.15. So generally, when we design the antenna initially, that okay, I should know the directly. Later we decide that okay, antenna directly close to antenna gain. That how much losses we can accept or we can tolerate. So first we decide that what is the pattern of the single element based on the Q factor, K factor, that K is 0.7, 0.8 and 0.9. So 7.47 dB. So this is the pattern of the antenna that we will decide that okay, if I'm an antenna gain is 9 dB, that K will be 1.1. After that, what will be the array activity? So by simple calculation, we decide okay, I want 20 dB gain. So 4 by 4 array antenna is required. Means 16 elements are required to get 20 or 20 dB gain. Keeping that single element gain is 7.16. Now 20 dB gain by 16 elements. So this is not compulsory that okay, 16 element can be configured in any manner, maybe in linear fashion. If I want 20 dB gain with keeping 7 dB element gain, if I use 1 by 16 element, I will get 20 dB. If I am using 2 by 8, 2 element in row, 8 element in column, it means 2 by 8 array. That means it will give the gain of 20 dB. Now 4 by 4, again 16 element will give the 20 dB. Now question is that which configuration I should select, 1 by 16, 2 by 8 or 4 by 4. So it depends on the beam width, because single element performance in both plane xz and yz plane are symmetrical, but in 2 by 8 or 1 by 16 beam width will be different or pattern shape will be different in xz and y. But in 4, because elements are same in xz and yz plane, that's why beam width will be equal. So depends on the beam width, we decide the configuration of the array, that 1 by 16, 2 by 8 or 4 by 4. So when we see the base stations, we see that these are the flat panel antenna. In that case, flat panel antenna all are not square shape of box type, all are in rectangular form. In that case, width is less, length is large. It means antenna elements are configured, because mostly base station antennas are covered in horizontal wide coverage, but in vertical they want less coverage. That's why number of elements in vertical direction are large. So beam width will be narrow in vertical fashion. In horizontal, number of elements is single. That means wide beam width. So you can increase the gain by increasing the number of elements by putting linear fashion. So gain is increased, but beam width will be narrower and vertical by keeping number of elements large in the vertical plane and in horizontal only single elements. So each antenna element now, okay, I am getting at both sides gain is 20 dB by 4 by 4 element. Now each antenna element can be controlled individually by phase or time delay. If I want to scan the beam, means I want to means 0 radiation in z direction. If I want to scan the beam means if I want to use in particular direction radiation. So by changing the amplitude, excitation or phase. So mostly scanning can be achieved by phase value. But if I want to save the beam, that I can use as a excitation, amplitude excitation change. So by changing the feeding, it is possible to construct a directed beam that can be repositioned electronically. Amplitude control can be used for pattern shaping. Means if I want to, when we put the signal from the satellite, our India is not a circular type of coverage. So sometimes we want to save the reflector, and sometimes we use symmetrical array, but changing the excitation by amplitude or phase, we can control the shape also. So amplitude control can be used for pattern shaping. And now amplitude and phase can be controlled in two fashions. One is the RF beam forming, another is the digital beam forming. So beam can be pointed to a new direction, narrow to widen in the microsecond. Depends on the excitation change mechanism by using DDF or RF beam forming. So an array that has a main peak at certain angle can also have, depending on the spacing between the antenna elements. These are the basic tool to design an antenna. Max strip line, as we know that, okay, depends on the impedance, dielectric constant and thickness. Because impedance is decided by the constant of the material and thickness of the material. So we should properly justify that, okay, my fabrication limitation is this, and to design a large width of the max strip line, keeping dielectric constant low or increasing the thickness. It means you are transmitting the power more, because width will large and also increasing the height. But mostly design guidelines say that, okay, in max strip line height should be as minimum as possible, width or dielectric constant should be high. But in patch antenna case, dielectric constant should be less and thickness should be more. So both are independent to each other or vice versa. Quarter wave transformer is used for impedance matching between one point to another point. Chamfer band is again a guideline when we are using a bending in the line, T-joint or Wilkinson or hybrid. These are the three configurations, or other configuration also, that which is suitable to design the array antenna. Basic T power divider, basic T power simple. This is the group type structure at high frequency that it may be radiate. So due to this width difference is more due to not suitable selection of dielectric constant and thickness. And unequal T power divider with quarter wave transformer. Quarter wave transformer is used for impedance matching like this. In this case, if this is the 50 ohm, this should be 100 ohm. Now, if this is 50 ohm, this is 50 ohm, it means this should be 25 ohm, because both are parallel. Now, if I want to that all ports are 50 ohm, then if this is 50 ohm, this is 50 ohm, this is 50 ohm, it means at this point 25 ohm and 25 to 50 ohm I should use as a quarter wave transformer. So all ports are in this case 50 ohm. Now, if I want to unequal T power divider with quarter wave transform, like that, if I want to, okay, so power is 1 by 2. It means this power is 1, power is 2 times. So width will also change because the impedance will, because impedance and port power are each port, like that. If this is the Z, it means Z into P, power is P. If I am getting P by 2, so impedance is 100 ohm. If this is 50 ohm, like this is 50 ohm, this is 100 ohm, this is 100 ohm, power is P by 2, P by 2. It means impedance and port power product is constant. So in design of the power divider, that power and impedance port should be equal. Temperament used for smooth flowing of the surface current, like this. This is the angle. So mostly we use 45-degree angle. Sometimes we use this type of configuration. Yeah, unequal and equal power divider, that 1:1, 1:2, 1:3. So by using some empirical relation, that keeping that R should be 100 ohm, that what will be the value of Z0 and Z02 and Z03, and unequal power divider 1:3. So sometimes we need that unequal excitation of the elements. Now, generally, these are the used in master line design, but when we use transmit antenna, that means square coaxial design, because this is the case in which antenna as a transmitting antenna, that master plan cannot handle the power. So we use this type of configuration. This is the hollow structure, that outer, and this is the solid inner. So like a coaxial, but in square nature. So because generally we don't use in circular. So square coax are used for high power application by giving the Z0. So this length A and this length B, keeping this air gap, we can judge that what is the value of A and B, keeping the gap. So gap is decided by the power handling capability, that we can increase the gap also to, and also multiplexation phenomena, and also PIMP, passive intermodalism product. So these are the passive intermodalism product is a very important phenomena, that any transmitting antenna I am using for high carrier power. That means due to line or discontinuity nature at the joint or dissimilar material, that both high power carrier will interact each other, and they will generate another frequency that falls in the C band, and it will catch by the LNA. So intermodalism product is very important phenomena at that case when we are using the antenna TX and RX. Now, we designed the 4x2 element patch array antenna at S band. That this is the three layer. First layer is the feeding network, green is the lower patch, and red is the upper patch. So this is the EM coupled. Again, this is the quarter wave transformer. This is the 50 ohm line. This is the 50 ohm line. I am using this T power divider. I know the use of this. I can use the Wilkinson power divider, but I am sacrificing the XLSO performance. But return loss bandwidth I am increasing due to this multi-layer or lower patch with the upper patch. Now, polarization is RSCP. Now, if this element, it means this is the zero amplitude, antenna is rotated physically, means in the direction of RSCP. So if I rotate this antenna like this, because antenna is RSCP, because this is the nearest point, first this will radiate, and after that this will radiate. It means RSCP polarization is the single. So I will rotate this element. So I will get this element position, and this is the feed point. of the single element. For this element, this is the single point feeding. Similar way, again I rotate this antenna with 90 degree, I will get this antenna. So point again is this point. Similar way, again rotation, I will get this point. So by physical rotation of each element, G is RCP. So physical rotation 1, 2, 3 and 4. Rotation in anti-clockwise. It means we will getting, this is the 50 ohm point of this element. This is the 50 ohm point in this element. This is the 50 ohm point at this element. This is the 50. Now, I want one angle 0, one angle minus 90, one angle minus 170 or by using sequential rotation. So this is the feeding point of this 1:4 power divider. If I say this is the input of these 4 elements, if this is the point, now nearest point is this. If I see that this is the nearest point, it means I am getting minus 6 dB with angle of 0 degree or some phase value. But with respect to this phase value, I am getting 90 degree delay at this point because this length is extra, lambda by 4 with respect to this length. So from this point, power is S21, means like that. This is the one port, first port, second, third, fourth, and fifth. But rotation. So I will give the pump the power. This will be minus 6 dB angle 0. This should be minus 6 dB with angle of minus 90 degree. And this should be minus 180 and this should be minus 270. So like that, from this point, this is the nearest one is minus 6 dB angle 0. This is the extra length lambda by 4. So minus 6 dB minus 90 degree. Similar way from this point to this point, because this feeding network is similar in this connection. Now from this point to this point, if length is like this length is y, this should be y plus lambda by 2. It means signal at that point is minus 3 dB angle 0, at this point minus 3 dB minus 180 degree. Now concluded is that minus 6 dB angle 0 at this point, minus 6 dB at minus 90, and minus 6 dB minus 180, and minus 6 dB minus 270. So in this configuration, XLSO performance or cross polarization completely cancel and co-polarization will be added. Now at this point, this is the 2x2 array antenna with sequential rotated with the broadband behavior in XLSO performance, also return loss bandwidth. Now again similar antenna is copied by keeping with this element spacing gap, and again both points are connected with equal power divider. So this is the main feed point. So this is the 2x4 LA arrangement in stack configuration. RSC polarization achieved by orthogonal edge feed technique. Lower patch is accordingly coupled with the maximum line. 1/8 corporate feed network is digitalized by designing 2 quarter wave transformer, again 15 ohm to 50 ohm and 100 ohm to 50 ohm. So in this is the 1 quarter wave transformer from 15 ohm to 50 ohm. Again this 50 ohm, this 50 ohm. So at this point 25, and this is the 50 ohm. So 25 to 50 ohm. So this is the another quarter wave transformer. So by using this type of design like this is the explanation of feed network design. Okay, this is the input actually. So I'm just explaining in this figure that amplitude is numerical value 0.25 means minus 6 dB with angle 0 degree because this is the nearest point. Similar way minus 90 degree from this point to this point. If this is the y, again this is the y plus lambda by 2. So I'm getting 180 degree. So 0.25 minus 180 degree and 0.25 minus 270 degree. Now, why it is not necessary that okay element should be 90 degree rotated. Element, if antenna element is rotated in any physical value, that same should be compensated by the electrical delay in the phase. So just I am giving the explanation that okay, this is the first element. So radiation of direction field from this direction to this direction. It means if you see that this is the green, green is the copolarization. So copolarization means RSCP. So direction of electric field rotation in this, but red is the cross polarization means LSCP rotation. So in first condition, you will get this type of electric field. After that, this field will move forward at this position, cross pole at this location. So like this, green move in this direction, clockwise, this will move in anti-clockwise. Same way, this element will be excited because 90 degree delay. So copolarization direction is this, cross pole will be in opposite. Similar way, in third, this will move is this side, this will move in this side. Similar way, this will move in this side, this will move in this side. So like this. So this is the copole direction, this is the cross pole. So like that. Similar way, in third element will be again copolarization direction. This green, 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 all are in same corner. This is the last condition. So if we see that green are the copolarization, so all will be at each other, but red are the cross polarization. So all are in orthogonal or opposite edge. Due to lambda by length, direction is opposite. That's why completely cancellation of cross polarization. So we can get good acceleration performance. This is the developed hardware. As 4 upper patch layer, lower patch layer. This is the feed network, and then beamwidth is again this beamwidth is narrower inside of 4 elements, and green blue is the beamwidth in y direction. Antenna elements can be located or can be positioned in different manner, rectangular. So like simple explanation dx and dy, number of element theta 0, theta phi. So rectangular fashion like that. One is the important is the triangular lattice. Advantage of triangular lattice is that that size will be less compared to rectangular because in this it will make it triangular. So distance will be same. Like that, if this dx, and this will be dx also. So in y direction, size will be less, keeping equal number of elements. So you can adjust more elements if I keep the equal size of the antenna in rectangular. But beamwidth will be different. Third, lattice is the circular lattice. In this case, beamwidth will be or pattern symmetry in all 5 planes will be good. But again, this is used mainly for phase array antenna because if I want to use design of feed network, very simple corporate feed network. In this manner also we can design the corporate feed network very easily. But in this, it is a difficult task to design feed network for this nature of position of the element. Now, another important parameter is the Grattan loop. What is Grattan loop? That condition, you know, that d is equal to 1 upon 1 plus sin theta 0 lambda. Lambda 0 upon 1 plus sin theta 0, it means spacing between elements should be less than lambda upon 1 plus sin theta 0. Theta 0 is the scan angle. So like that, just I try to that 8x8 array antenna, I want a scan angle 30 degree. That spacing should be less than 0.66 lambda as per formula given by this. Now intentionally I am giving spacing 0.8 lambda. So I am getting to get what is the directivity 23.90 dB because so power in another direction will be same value or some less value, but order of 2, 3 dB or 4 dB down. So this is the unwanted signal or unwanted power that I'm giving the pumping of the power in this direction. So there is no need. So I should decrease or I should follow the. So this is called as a grating loop. This is called as a main loop. So if I keeping this 0.65 lambda, earlier I put 0.8 lambda, I am giving 23.90 dB gain by 8x8 array antenna. Now decreasing the spacing 0.65 lambda, grating loop will disappear and we are getting 25.12 dB gain. So this is the guideline that okay, when we are designing the antenna to scan the beam, that we should follow the. Another important parameter, the mutual coupling. That if I want to scan the beam of the antenna, as per previous scenario, that okay, I want 30 degree scan angle or 45 degree, 30 degree scan angle, I need 0.66 lambda spacing. When we are, because we are putting the elements nearby, so all elements will be in near field. So in that case, we cannot increase the gap or spacing, because if I increase the gap, that means you are creating a grating loop. So mutual coupling will exist because both elements are nearby. So element pattern of the antenna changes from its free space value when it is inserted into array. The effect will be different for each element of the array. It may be necessary to use the concept of active element pattern. When we use the spacing between element, that means due to interaction elements pattern, degrade the performance. What will be the performance change? Means you will lose a return loss or frequency shift. So frequency shift can be changed, okay, by readjusting the dimension of the antenna. But again, what will be the active element pattern? Active element pattern means keeping all element as a conductor, and what will be the radiation pattern of the center element? That is called as a active element pattern. That pattern will degrade. So by keeping some arrangement to reduce mutual coupling, we can increase the return loss, active element return loss performance. So mostly when we scan the antenna 30 degree or 40 degree or 50 degree, we use active return loss should be more than 12 dB. If active return loss is 10 dB or 8 dB or 7 dB or 6 dB, your element pattern will be degraded. So by different techniques, we can reduce the pattern. Scan blindness is another phenomena that okay, sometimes due to nearby element, that due to near field scattering, pattern will be subtractive. In that case, in particular direction, you will get a null. That is called as a scan blindness. So direct consequence of mutual coupling, due to mutual coupling, that pattern will be degraded, can result in complete cancellation of the radiated beam at some scan angle. Occurs when most of the central elements of the array have reflection coefficient close to unity. It means it means reflection coefficient unity, it means no excitation. That means antenna element is not contributing in the array factor. Again, antenna array, planar array, like in this fashion, this configuration used in our IRNSS as a linear array. Yeah. So like this, number of elements based with the element phase. Beam is scanned in different direction. Now, like this is the grating loop that it is increasing by keeping the increasing the spacing. So this is the another that I am increasing the spacing 0.62, 0.63, that this grating loop is increasing by keeping number of elements increase. Beam width is narrow, so 0.8 to 0.83. The scan angle is 30 degree, 0.95 lambda equal. Another from 3.40 to 3.17. This is a linear polarized antenna, linear vertical polarized antenna. Gain is 19.16 dB. This is the another development of isoflux antenna. Should I continue or hello?
Sir, actually the time is still 6 o'clock.
Okay.
So if you like, we can take the queries. Swati?
Yes, sir. Sir, can I say the questions on behalf of participants?
Yeah.
Okay. Sir, the first question is, which type of chamfered band is best for the surface current distribution?
When width is very small, like order of 0.3 or 0.4 or 300 micron or 400 micron, I will use this type of band. But when width is large, keeping of 1 mm or 2 mm, like in glass epoxy 1.6 mm, I'm designing 50 ohm line. So I will prefer that angle, chamfered angle, this angle should be 45 degree. So by effect of this, generally at S12 from 1 to 2, so we use in small bit, we use this curve band. But when width is large, we use 45 degree chamfering. Or we can see the performance also that okay from S12. So mostly and we use this type of band, but at L band, S band, C band, we can use this chamfered band. But depends on the width of the line.
Okay, sir. So can I ask the next question?
Yeah.
For satellite communication, what is the minimum desired gain and what is the preferred material of the substrate and radiator?
Okay. देखिए mostly our satellite, because satellite provide the radiation capability over the earth. So mostly antenna earth cover in. If I say that one example that our geo satellites are around 36,000 kilometers. Okay. Now whole earth is covered only 17 degree. It means I need radiation capability of the from the satellite is should be within 17 degree. It means if I am pumping the power after 17 degree, there is no meaning of the radiation. Okay, so my antenna gain is decided by the power of the generation in the satellite. So we decide, okay, my power generation is 300 volt or 200 volt. Due to some path losses, antenna gain is decided. And also we know that antenna gain is decided by the our area of the okay, aperture area. So our antenna capability like 2.2 meter 2 meter antenna we can provide solution. So keeping this 2 meter antenna at different frequency band, we decide the gain. So at S band 0.9 meter antenna, 1 meter antenna, or if I say GSAT satellite, that we have given 6 meter antenna, unfurlable antenna, that gain is 45 dB gain. So depends on the application. So mostly all satellites have more than 20 dB gain, but at UHF band, gain is only 12 dB. So at KU band, gain is 30 dB, approximately close to 30 dB. At C band, 25, 27 dB gain, and reflector antenna give 35 dB gain, or 6 meter reflector antenna is giving 45 dB gain. Now, that your question is that, okay, when we design a patch antenna, okay, so first requirement is that antenna broadband, we can generate the pattern or generate the polarization. Now, in dielectric constant, first thing is that loss tangent should be minimum. It means we are using RT6002 material. RT6002 material. Why we use RT6002? Because loss tangent is very less, 0.0009, dielectric constant 2.94 or close to 3. Now, third, selection of the material, the coefficient of expansion in X, Y, Z direction should be approximately equal. X, Y, Z expansion. That means over the temperature, what will be the expansion in the dielectric material? So X, Y, Z is value of 1724 ppm in this material, RT6002. Now we have qualified another material also, dural material, that RO3003 also. We can use this material also. DK10 also, RO3010. And another important parameter, TML, CVCM, WR. These are the three parameters: that total mass loss, water vapor regen, or collective volatile condensable mass. These are the three properties of the material that should be qualified. That because antenna will work in vacuum, so no mass loss should be exist, and temperature range also, because our temperature in satellite comes from -72 plus 110. So antenna material properties should be sustained, means dielectric constant and loss tangent. So these are the basic properties to use the material. But thickness wise, this is the design guideline that, okay, 20 mil, 10 mil, 30 mil. But electrical and mechanical property means dielectric constant, loss tangent, but TML, WVR, CVCM, and also expansion of thermal coefficient of expansion, TCE, in XYZ direction.
Yes, sir. Sir, next question is, how can we calculate impedance of a particular antenna port in any simulation software? Means impedance at a antenna port where the port is connected. For any of the like HFSS or CST, how you calculate, sir?
When we divide, when we are doing in HFSS, in master line, the lump port and wave port. Okay. So lump port, when we are defining 50 ohm, so you can renormalize the impedance. If I just want to say that, okay, line is 50 ohm. Okay, I don't know, line width is kept with respect to 50 ohm. But I have defined the lump port keeping that it is 50 ohm. So I am forcing that this impedance is 50 ohm. Now, if return loss is getting good, it means impedance match with the line. If impedance is not matched with the line, your return loss will be poor. Now, again, without any disturbance of this, okay, just I am taking an example that width, glass epoxy thickness is 1.6 mm. Okay, now width of the 50 ohm line is 3 mm. Okay, now if I keep width of the 2 mm, put a lump port, and forcefully I am saying that this is the 50 ohm. But again, I kept 2 mm width, but it should be 3 mm, but I kept 2 mm. It means I know the theory that, okay, due to 2 mm, impedance will be large because width is less. So more than 50 ohm, maybe 70 or 80 ohm. But you are giving the impedance 50 ohm. You are saying to software, okay, this wave port impedance is 50 ohm. Now see the Smith chart. Definitely it will close to, now if it is width is 2 mm, I know the value that it is 70 ohm. Okay. Now your graph Smith chart plot will close to 1.4, not at 1, because 1.4 multiply 50, it means it is 70 ohm. So by seeing the Smith plot, you can judge the impedance of the line. Now with the Smith chart, okay, Smith chart point is at 1.4 value of R. It means 1.4 multiply 50, it means impedance is 70 ohm. So now again, I am renormalize the impedance with the 70 ohm. Your plot will be shifted at 1 because you have normalized the impedance with the 70 ohm. And then you will get good result. So by checking the Smith plot, you can see the, or you can judge the impedance of the line. Yeah. Are you clear?
Yes, sir. So next question from the participant is, what should be the minimum required SNR for satellite communication?
SNR, so signal to noise ratio. Hello?
Yes, sir. Yes, sir. Signal to noise ratio.
Okay. Signal to noise ratio is not a antenna property. Signal to noise ratio is the property of the amplifier. So we don't worry about the signal to noise ratio. Antenna noise temperature is important role in the equivalent noise temperature. So we should know the noise temperature, not signal to noise ratio, because antenna noise temperature is very important to calculate at the time of GYT. GYT means antenna gain and temperature, noise temperature, equivalent noise temperature. So signal to noise ratio is not a parameter of antenna. Okay. Now equivalent noise temperature is given by different noise temperature. It is given by the noise figure of the behavior. So T0 F minus 1. So it is not dependent on antenna. So system noise temperature is independent with respect to antenna. Now TS plus antenna noise temperature is called total noise temperature. Now antenna noise temperature depends on the radiation capability. That antenna is looking towards Earth or towards satellite or towards space. Now, if I am giving the if antenna is radiating towards space, if antenna's beamwidth is very narrow, like low gain antenna, it means antenna noise taper, noise temperature considered as 70 degree Kelvin, because antenna noise temperature depends on the radiation coverage. So mostly when we use satellite antenna, that we use 300 Kelvin for satellite antenna because it is fixed. But our from the ground station or ground antenna, low gain antenna, mostly we use 70 degree Kelvin because due to wide beam width. So up to 70 degree. So one curve is given in lot of books that okay depends on the bandwidth. The your low gain antenna and medium gain antenna or high gain antenna depends on the beam width or age taper. So in my opinion that signal to noise ratio is different with the antenna. The noise temperature I should know.
Okay, sir.
Yeah.
Participants can ask the question if you have any more doubts. Sir, I think at present no more doubts are there. Thank you very much, sir. On behalf of EICT Academy and MNIT Jaipur, thank you for
Just I'm interrupting.
yes, sir, please.
This antenna within 10 minutes, they will explain. So
Yes, sir.
allow me that I can just give some glimpse of this antenna. Oh,
Yes, sir, please. You can
yeah.
see.
This is the isoflux antenna. Isoflux antenna means antenna system that energy of uniform strength over the coverage region. In navigation services, that mostly our antennas are cosine pattern, means at the center from the satellite, the antenna gain is more and antenna gain is reducing with respect to different theta cone angle. Now, pattern shape, I want to use this type of pattern that is called as a isoflux pattern. What is the meaning of isoflux pattern? Means that our earth is nearest to the satellite and gain is more. It means I will get more power in this region. Same antenna at the ground at this point, because in this direction gain is also decreased and also path loss is also decreased. It means you will lose the power with keeping equal antenna at both location. Like this point, similar antenna, if like antenna is at that point, antenna is this point, in that case, you will get more power at this region and you will lose the power. Now, so I should compensate both of these two. In this case, I will decrease the gain at the center and increase the gain. So from the geostationary satellite, tip of 1.3 dB at the center of Earth from the satellite to cover the entire. So these are the relations to compute this value by this calculation, that okay, what will be the look angle. So we have designed this antenna at Allen Desmond shared aperture dual band isoflux array antenna, keeping that Earth's radius is this 36,000 kilometer, R satellite, Nadir angle, slant range, path loss difference in dB. So maximum path loss difference is 1.31. It means I will decrease the gain at the center with respect to this 1.3 dB. So we have done some array analysis by keeping the different positions, location of the elements. So this is the some code. Now, finally, just I want to say that, okay, this is the configuration. So I am using 4 circular ring. First element, first ring, 6 element, then 12 element, 18 element, 24 elements. And these are the positions and these are the 1.3 in the center. Now, by changing in first ring, amplitude excitation is 0.7, phase is 0. Second ring, amplitude excitation is 0.62, phase is 0. Third ring is 0.55. It means less excited with respect to first and second ring. Then again, phase is 0. Similar way, in fourth ring, amplitude is 0.4. 1, 2, 3, 4. Fourth ring is amplitude is 0.4, keeping out of phase. So in this case, excitation amplitude means excitation amplitude is changing, also phase is changing, but first, second and third ring are equal phase, but fourth ring is opposite phase. That's why so first, second, third ring, fourth ring. So total elements are 60. Now, blue, red, green and yellow. 6, 12, 18 and 24 element. Total elements are 60. 7.6240. outer ring is out of phase. This is giving this type of pattern, keeping that 1.3 dB gain at dip in the both side and gain at large at this angle. Now, really, this is the that means can be reduced number of elements because number of elements are 60. So we use array thinning. Again, I remove the third ring and change the again coefficient excitation. Then I am getting similar performance. That third ring and fifth ring reduce the 6, 12 and 24. Total elements will be 42. Excitation 1, 1 and minus 0.2 means minus 0.2 means amplitude excitation is 0.2 with respect to 1. Less excitation but opposite phase. Because this is the high power element and now reducing 53.33% element, that power element in each element 6.5 watt because power is high and 250 watt at L band, S band and L band is 150 watt. So based on the power distribution, we compute the value that each element can handle easily. So by keeping patch element in circular polarization. Now, another configuration we did helix antenna. So if you see that S band helix are red, blue are the L band helix antenna. Some shared elements that are used, and this is the green is the S band, again square coax reading network. If you see this, all sequential rotation applied because these are the 1, 2, 3, 4, 5, 6 elements. So 60-degree rotation with 60-degree electrical phase is applied, and then acceleration performance is good for both L band and S band. So red is the L band feed network, green is the S band feed network. So mostly GPS satellite isoflux pattern, but recently we will float this antenna for isoflux pattern. Right now our satellite is the cosine pattern. So these are the performance at L band. Acceleration performance is, if you see the 17 dB or this is the 30 dB means close to 25. So performance is 42 dB difference. Return loss better than 30 dB. Similar way S band performance. Yeah, thank you.
Sir,
Any other question?
sir,
Yeah.
where we can find all these typical values of the parameters for satellite and space communication? Is there any like website or something?
We don't disclose the antenna performance or what is the parameter. Frequency you can get, but if you want interested, anybody are interested, we can give the task to them. Okay, this is the requirement. If you have some solution related to these value, most welcome. You can design, but in website or we don't have any data.
Okay, sir. Sir, I think only these many questions are there.
Like anybody can ask me. So even another antenna. Okay. So these are my contact details. So anybody can contact me to any help related to fabrication, design, and all, and even testing also. I can support return loss measurement, insertion loss, even radiation pattern also. We have some battery facilities, the anechoic chamber, CATF. So anybody can contact me.
Yes, sir. Oh.
So if any question, anybody can ask. Otherwise, he may ask later. Or
Sir, only these many questions are there at present. Now, no more questions. Queries are from on behalf of participants at present. Sir, on behalf of EICT Academy and MNIT Jaipur, sir, thank you very much for the session. It was very wonderful and fruitful for all the participants.
Sure. Close?
Yes, sir.
Oh,
Dear participants, tomorrow from 9 o'clock, we are going to start the first session of the day 8. You are requested to please join by 8:45 a.m. Thank you.